Hi everyone, so my name is Elisa, and today I'm going to give a talk on understanding backpropagation in PyTorch. And before I begin, I think that there will be some people in this room who's very familiar with the topic, and there will be some people here who are kind of here for the free pizza. So I'm going to try to summarize the main points for just some main takeaways, so that even if you're not really well-versed in this area, you can still learn something from this presentation.
Just fine. Click on your PowerPoint with the mouse and that helps.
Also, it's okay to be here for free. Okay, so first of all, what is PyTorch? So PyTorch is a Python package that's used for deep learning. So PyTorch and TensorFlow are kind of the most popular packages, but in my opinion, I think PyTorch is most popular for building customizable deep networks, and it's free and open source. Yeah. So today I'm going to first I'm going to start with kind of a set of prerequisites that I expect for the audience to kind of know about neural networks and optimization, and then we'll talk about backpropagation and what it is. And then we'll talk about how we implement backpropagation in PyTorch. And then we'll kind of go very lightly into how it's implemented algorithmically and take a little bit of a peek into the source code of PyTorch. So let's start with kind of the prerequisites for kind of what I might expect the audience to know about neural networks to begin with. So first of all, hopefully we all kind of know what a neural network looks like. So it will be made up of an input layer and an output layer, and then there's any number of hidden layers in the middle, which can consist of any number of neurons. And this is just your feed-forward, fully connected network. There's no extra bells and whistles to this network. And so we expect that basically every value in the input layer should go to every value or every neuron in the first hidden layer, like this. And in each neuron in the hidden layer, we should perform some type of linear function, Wx plus b. And yes, it's in red. And then we try to wrap it oftentimes into a non-linear activation, like a sigmoid or a tanh or a rectified linear union. And that's really the key to neural networks, because we already had linear equations for a very long time, linear models. And we even had nonlinear models, but a neural network is able to create these really complex nonlinear models, which can really fit our data really well. So that's why we like them. So after we wrap it in the activation, we send all the outputs from the first hidden layer as inputs into the second hidden layer, and so on and so forth. We calculate this linear equation, we wrap it in a nonlinear activation, and then it gets sent to the output layer, where some final calculation will be made, and then we should get either like a regression value, or where we might predict a binary class or some type of multi-class output. So how do we measure the performance of our model? So we want to know if our model is doing well or not doing well. So we can use a loss function or a cost function to do this for us. And you might read some computer science papers and you see that the loss functions are really complicated and confusing. But at the core of pretty much all of the loss functions in a computer science paper, it will be made up of one of these two loss functions, either a mean squared error or a cross entropy loss. And I'll highlight mean squared error because even if you worked with linear regressions, you've seen a mean square error. Basically, you're taking your predicted label from the network. Sorry, I had to shaky. Taking your predicted label from the network, and you're subtracting it from your ground truth label, and then we square it because we want to make it differentiable. And so that's how we can measure the performance of our model. But it turns out that loss function is important for more than that. It's important for optimizing our network. And so if we have this network of a bunch of weights in our neurons to perform this linear functions, we want to be able to get the exact values of the weights which can correspond to the lowest possible loss. So this is completely an optimization problem. And so in a simple example, In a simple example where we have only 2 weights and we're using the mean squared error, we can actually graph out all the possible values of our loss function, and we can see which values of weights out of all possible values would result in the lowest possible loss. And so this is what we're doing in optimization. But we know that neural networks are much more complicated than that. We can't just look at this graph. We can't just look at a graph and see where the lowest point is. And we have these really highly nonlinear functions where there's going to be more than one minimum. And so we need to do a more sophisticated process for that. And so we might do something like gradient descent, also known as steepest descent. And there are 2 core steps in a gradient descent algorithm. We want to, 1, find the best direction, and finding the best direction means calculating a derivative or a gradient. And we want, basically the direction is going to show us which way should we lower our weights in our neural network that will result in a lower loss. And then we want to move a small step in that direction. So that's this alpha wi for each weight. So find the best direction, update the weights. And backpropagation comes into our talk because it turns out that using this method called backpropagation or backwards propagation tends to be the best way to do this optimization process. And it means that we basically start in the back of the network, and then we find the best direction, we update the weights, and then we work our way up. So we find the best direction, update the weights, and do the same thing. Okay, so that's optimization and backpropagation. So if we could actually view what gradient descent is doing, this would be in a situation where we have only 2 weights because we could view it in 3 dimensions. It would look something like this. It would be slowly, the values of the weights that we choose would slowly inch their way along until it reached the lowest possible value for the loss function. A small technicality is that because the function is so nonlinear, there are so many different minima that you could fall into, and we call those local minima. And the global minimum, which is the lowest possible value for our loss function, sometimes we never find that, but we just want to get the weights to a point that the model does good enough for us. So any local minima that does good enough is really what we're looking for. Okay, so we talked about gradient descent, and we talked about how the first most important step is to find the best direction. So finding the best direction always means we want to find the derivative of the cost function with respect to each weight in the network. And I'm going to show some confusing notation, but there are 2 main takeaways I want you to learn from this. The first one is that it's not a mystery, it's not a black box. We know how to do this. You can do this on paper. You can write it all out. You can calculate the derivatives yourself. And I mean, you can use these equations here. But the second point is that you don't want to do that, because if you did that, you might be very likely to, first of all, mess up. Anytime you add a neuron into your network or you update your loss function in any way, you're going to have to recalculate that all over again. And also you can imagine that in modern day neural networks, you might even have billions of different weights in your network. And you don't really want to be calculating this for a billion different weights. So just know that's possible, but you don't really want to do it. And so that's why it's good that PyTorch does it for us. But let's just take a quick look at it. So basically the main hallmark of being able to calculate these partial derivatives is using the chain rule. And hopefully everyone here knows what the chain rule is, but basically it's a special trick that you can use when you're calculating derivatives if you have a set of nested functions. And if you look, if you look at the end of the neural network, you can see that basically the whole network is just a set of nested functions. And so that's why we can really take advantage of the chain rule. And because it's a set of nested functions, you might also see, oh, that's also why backpropagation makes sense, because we have to start at the back and kind of work our way forward through the nested functions. So someone was able to actually summarize all of the partial derivatives you need to take with 4 different functions. I'm not going to like go through it all in depth. I just want you to see that it's possible. So this is calculating the partial derivative of the cost function with each weight. All you would need is the activation of the previous layer, and then you would multiply it times this delta function, which consists of weights in layers that are closer in this direction, which we call upstream, until you get to the last layer. And then you could also calculate, there is an equation for calculating the cost function with respect to the biases as well. But main takeaways, you can do it by hand, but you don't want to, and you use the chain rule. Okay, so how do we implement this in PyTorch using some code? So let's first take a look at neural networks, because everyone likes that. So first thing we need to do is create a network architecture. And so we always create this network object using a class, and we define all of our layers in the initializer. So this is where we kind of define whether we're going to use linear layers or convolutional layers, etc. And then we have a forward method, and this defines the forward pass. So we define our layers here, but we need to define how the input is going to go into each of these layers. And so that's what the forward method is for. And then we have the training step. So the first thing we're going to do is we're going to call up our model. So we're going to create a model instance here, and then we are going to define our optimizer. And so here we're using stochastic gradient descent, and we're going to optimize the parameters of the model. And then we can define the learning rate. There's other bells and whistles you can add to the optimizer, but I don't put them here. And then we have our actual training loop. And so we iterate through epochs. First thing we need to do is we need to set model.train to true. And basically what this is we're telling PyTorch that we are ready to train the model. And this is mostly important if you have things like batch normalization or dropout in your model, because they kind of depend on knowing that your model is training. If you're trying to evaluate your validation set or your test set, you would set model.train to false, or you would set model.eval. And then we're going to iterate through all of the batches. So oftentimes we use what's called a data loader, and the data loader helps us to organize our data, our input data, into batches for the model. And then we're going to get our model predictions in this step here. Oh, sorry, for people over here. And then we're going to calculate the loss. And so PyTorch has its own built-in functions like mean squared error and cross entropy loss, but you can also define your own. And then the most important step, we're going to backpropagate in these 2 steps. So we're going to call loss.backward, and what that's going to do is it's going to calculate all of the partial derivatives of the cost function with respect to all the model parameters here. And then we're going to call optimizer.step, and that's the step that's going to move the weights in the direction that we just calculated here. And then if you do this right, you should hopefully see your loss decreasing. And because in this example, we use the stochastic gradient descent, you might see it looks a little bumpy. Your loss sometimes might increase a little bit, but overall the trend should decrease. So another method that I want to kind of talk about is torch.tensor.requires grad. So So the model parameters are set in a data type called torch.tensor. And that data type also stores an attribute called grad. And grad is where it stores the gradients, basically. And sometimes we don't want to store the gradients. Sometimes it's just a it's just using up memory, but we don't want to backpropagate through those values. And one example of that is if I'm using a set of pre-trained weights and I don't want to update them, I just want to freeze the network. So then I can use this method called requires grad. So if my torch tensor is called x, I just say x.requires grad false, and then it just won't store anything in that grad attribute. There's another couple of methods I want to kind of distinguish. So we call loss.backwards. This is using torch.autograd. We call loss.backward, but you can also call loss.grad. And the difference is just that with .backward, what you're doing is you are calculating the gradients and then you're storing them into that grad attribute. But with grad, you're just going to calculate gradients and it's going to return the gradients to you as output. So let's do one more example of using torch.autograd. You don't need to use it in a neural network. You could just do it to calculate a derivative for you. Like let's say you don't have Wolfram alpha, or you have access to it, or you just want to be cool and use this in PyTorch. So you can totally do that. Here we're giving a concrete value to x, which is 3.6. We're setting our function to the x squared, x times x. And then we are calling our function y dot backward. And then we're going to take a look at what was saved in the grad attribute. And it turns out that what's saved is 7.2, which is equal to 2 times x, which is equal to the derivative of y. So this is how we use it to calculate derivatives. All right, so let's lastly talk about how backpropagation is implemented algorithmically. And before I begin, I want to thank Justin Johnson, who is a professor in EECS. He has a lot of content on PyTorch, and that's how I learned some of this stuff from him. And I borrowed some slide content from his slides. Okay, yeah. So in order to understand how we implement this in PyTorch, we should understand what computational graphs are and how to use them. So a computational graph is a way that we can kind of graphically represent some equation. And it helps us to firstly structure our equations more clearly compared to writing it out on paper, but it will also allow us to use backpropagation to leverage gradients. And it has this cool kind of trick where we can calculate gradients for all the variables using only what are called local gradients. So first, let me explain. Here's one example function. It's f of these independent variables x, y, and z, and our function is x plus y times z. So this is a DAG or direct acyclic graph, and we can see x plus y, the arrows, times z equals f. So this is a computational graph representation of our function f. So let's run through some example of how we would use a computational graph. So I'm going to set some example input through our forward pass here. So I'm going to set x equals to 3, y equals 4, and z equals 2. So I'm setting values into our function. And I'm also going to define a kind of an intermediate variable q, which is going to equal x plus y, and that equals 7, because 3 plus 4 equals 7. Okay, so we're gonna backpropagate through this computational graph. And we're gonna start at the end, because that's what we do. So we're gonna take the partial derivative of f with respect to f. So that should be equal to 1, right? Because it's derivative with respect to itself. Then we're gonna move back one of the, we're gonna move back one of the nodes here to look at q. And we're going to take the partial derivative of f with respect to q. So f equals q times z, because we defined q as x plus y, so q times z. So the derivative of f with respect to q should be z, right? So z equals -2. So the derivative here is going to be -2. We're going to go, oh, here's a good time to also add some definitions for you. So we basically call, so if we're situating ourselves at this part of the graph q, we can call any gradients which are in the direction towards the output layer as being upstream gradients. And any gradients which are in the direction towards the input layer are going to be called downstream gradients. Okay, so now we're going to do this node here, the partial derivative of f with respect to x. And you might be tempted to, if you're already thinking this in your head, to just take the partial derivative using the whole expression of f, but we're not going to do that. We're going to use a chain rule, and we know that partial derivative of f with respect to x is going to equal f with respect to q times q with respect to x. That's good. Yeah, so some calc 1 exercise for you. And we already calculated partial derivative of f with respect to q. It's -2. So all we need to do is get q with respect to x, and that's going to equal 1, right? So we just say -2 times 1 equals -2. And then we basically use the same principle, apply it to y, same exact chain rule. And then lastly, we're going to look at z. So f with respect to z. So we know that f equals q times z, right? And so the derivative of f with respect to z is going to be just q. So that's what we put here. So notice that when we were kind of backpropagating through this graph, we only really need to think about nodes which are the values of nodes which are adjacent to the node that we were looking at, or the node which is directly upstream of our node. We never actually have to go any further than that. And that's what we call this, area the local gradient. So any node which is adjacent to or directly upstream of the node we're looking at will be called our local gradient. And that's really the advantage of using computational graphs when we're backpropagating, is that we don't need to worry about calculating a derivative over the overall expression. We only need to look in this local area to calculate our gradient. And so that's the main takeaway. Like, even if you didn't follow everything about the computational graph, the main takeaway is that we can really leverage these local gradients so that we don't have to do all these calculations based on the overall expression. And secondly, even though I showed you this simple example, all of the more complicated examples I can show you work in the exact same way. And so here's another graph that we can look at. But what I want to say now is that now that we know how this works, now that we've kind of taken a look at both the forward pass and the backward pass, we can write this up in code, and we can define a function which gives us our forward pass, and then we can write up a function which gives us our backward pass. And if you become really good at this, you don't really even have to do any math anymore. All you need to do is you just kind of understand what the operator, what's the kind of trick at the operator, which gradient are we trying to take, or what calculation do we need to make, and then we can just use that in our backward pass. So I put this box here to show, okay, this part of the graph, here's where it's represented in the forward pass, here's where it's represented in the backward pass, so on. Yeah, so basically, after a while, you don't even need to use paper at all. You don't need to do any type of calculations. However, once we start to scale this up to tens or hundreds or thousands or even millions or billions of parameters, you don't really want to be doing this by hand, no matter how easy it is to do. So thank goodness that PyTorch does that for us. And they do that by, since we know that the behavior at the operator of calculating this forward pass and this backward pass are predictable, we can define the behavior at that operator. And so if we go into, this is the old PyTorch code for the sigmoid operator, we can see code for the forward pass, and we can see a section of code for the backward pass. And so this is kind of an algorithmic, or what do I say? This is some kind of a shorthand for how to calculate the derivative of a sigmoid function. So you can just define the behavior at each operator. And this is so I actually tried to find this code, but it's the old code, and they rewrote it, but it's more clear to see where the forward pass is, where the backward pass is. So you can see how they define that, and you will see if you look in their code that they have definitions for all of the operators that you can use in PyTorch. This is their old code, and if you want, which I have a link to if you're interested, but I also have a link to the new code where they define all of the operators as well. Okay, so a section summary, computational graphs. So PyTorch real-time gradients are made possible by leveraging these computational graphs. So we had a look at how to use a computational graph, what it is, and then we also saw what the benefits are of using computational graphs. They allow us to backpropagate by only focusing on these local gradients rather than calculating partial derivatives over the entire loss expression. And it's kind of this algorithmic trick so that we don't have to do a bunch of math on paper. We can just look at this over a short area. And the other advantage of that is that it's able to calculate gradients in real time. So anytime that I'm going to modify my network, like add some neurons, add some layers, or change my loss function, it doesn't have to do a whole lot of extra preparation to calculate the gradients, because it's just always going to follow along whatever graph you've made. So yeah, presentation summary. So we talked about backpropagation and optimization. So backpropagation was a method or algorithm used for finding gradients in the network. We remember that gradients help us find a direction to travel down to reduce our loss. So backpropagation consists of calculating partial derivatives at the back of the network first, and then moving forward. We looked at code implementation of PyTorch. So we saw, okay, this is how you set up a network. This is how you go through the training loop. This is lost out backwards, and the optimizer does that. And then the algorithm implementation. So we looked a little carefully at how PyTorch uses computational graphs, and it allows this real-time calculation based on local gradients. And we looked a little bit at the source code and saw how they define these operators, which help us do backpropagation. And so I'm just going to end this presentation with some additional resources in case you weren't able to catch all of that. And I'm going to make a shameless plug for my blog. So one thing I enjoy is I want to read some deep learning papers, and I like to kind of just share what I've learned. And so I put this whole presentation into a 2-part series there, so you could take a look. And if you don't want to, there's a whole bunch of other good resources here. So yeah, thank you. Are there any questions about anything? Yeah.
So if you're training a complex neural network, and you're using backpropagation, my understanding is that you will often end up in a local minimum from what you're presenting. So does that mean we should run the training process many times to try to get to the lowest local minimum we can find, or how do you address that problem?
You can do that, but hopefully, so I kind of skipped over how there's other bells and whistles to the optimizer, but there are kind of these other tricks that people do to try to get out of local minimum. So over here, so we have things like momentum, which is supposed to kind of like, if you're stuck in a local minimum, it's supposed to kind of push you out a little bit. Yeah, or for example, we can use things like schedulers or weight decay, which can help us to reduce our learning rate. So that would help us so that maybe in the beginning we're jumping over big local minima, and then once we kind of reach a good spot and we don't want to jump over anything, we start to reduce our learning rate more and more and more and more, so that we kind of reach the best minimum we can find. So there are some tricks for that, but you can rerun it. But usually I think if you're finding that you had to rerun your network to get like a much better performance, then you probably didn't make your network very good. So probably you'd have to restructure it.
Yeah, there's an online question from Hui who asked, how are non-differentiable functions such as ReLU handled?
Yeah, so in optimization, so like actually for functions like ReLU, there's something called I think it's called like a sub-differential or something, where basically even though technically there's no you can't calculate a derivative at that point, there's actually like a whole set of derivative of possible choices of derivatives that it could make. You think about the tangent that would form at that elbow. There's a whole bunch of lines there that won't touch the function. And so that whole set is actually a possible derivative. And so usually at that point, in the code for the operator, they will probably just like pick one. They'll pick one of the possible set of derivatives.